we were talking about algorithms in the lecture for week 4, and we talked about a number of algorithms. One that we talked about had to do with finding a target value in an array that might be in there, or in finding a name of a contact in a phone book, and how we can achieve that efficiently. We also talked about one of the popular algorithms for finding some data requires that the array is sorted in some fashion. And the one we talked about a lot was the case where the data were sorted left to right for numerical values, and then how to achieve that. And we looked at several algorithms. So this tutorial, if we just look on week 4, is about the bubble sort. And it looks like this on the tutorial tab for week 4. So what this tutorial is going to go through is just a heuristic feel for exactly how bubble sort works with an explicit, very simple example that we look at the array for the whole time the bubble sort's acting. And the idea of this is to move through an array a couple pairs at a time, and just compare pairs in magnitude in our array. And the idea in general is that if we find a pair that are out of order, we're going to move by swapping the higher value to the right and generally move the lower value to the left as we slide our window of comparison down the array. And in pseudocode, that practice of writing your thoughts and the logical steps to develop algorithms, looks like this. And I should say there are some other implementations possible to correctly construct the bubble sort algorithm. But this is a popular one. This adheres to style guidelines. It's very concise. It's correct. So this is a good one, a popular one, and it's a classic, so keep that in mind. First thing we're going to do is we're going to initialize a counter. And the counter, we're going to use the counter to identify a stopping condition when our array is already sorted. Okay, so it's a counter for the number of swaps we make as we go through. And we're going to initialize it, setting it to some non-zero value. Now you could set it to any non-zero value. Zero, if we go through the whole array and we make 0 swaps, we stop, right? That's our stopping condition. So we could initialize this to any value other than 0 if we set it up like that. It's traditional if we're going to count an increment, we count things in the positive integer. It's traditional to set a counter like this to -1. That's a value that a count could never take. And so we know that that's the initialized state. And we might use that, for example, to do problem solving or bug tracking. We haven't talked about that yet, and we haven't done it yet, but that's what it's for, and we may come across that in this module. So the qualification for the loop, we're going to implement some sort of loop, and we're going to repeat it until the swap counter is at 0. Remember, it starts at -1. So the first step in our loop is we're going to set the swap counter to 0, so that we can count how many steps that we go. We're going to look at each adjacent pair one at a time, and if the two elements are not in the right order, we're going to swap them, and we're going to increment the counter by 1. So maybe we have a beginning state like this. We have an array of some numbers, very simple array. Our swap counter is set to -1. What's the first thing we do? We set the swap counter to 0. The second thing we do, we're going to start our sliding window of comparisons. We consider 5 and 2. They're not in order. We're going to swap them, and we're going to increment the swap counter by 1. Boom. Now we're going to slide our window. We're going to compare the two numbers, 5 and 1. They're not in order. So we're going to swap them, and we're going to increment our swap counter by 1. Boom. What are we going to do now? Our swap counter is not at 0. We're going to slide our window to the next pair. We're going to compare their values. They're not in order. We're going to swap 5 and 3. We're going to increment the swap counter by 1 to 3. Boom. We're going to slide our window. 5 and 6 are in order. Now this time, since they are in order, we're not going to increment our swap counter. We're just going to slide to the next frame. Boom. And finally, 6 and 4. We're going to swap them and increment our swap counter by 1. So it should equal 4. Boom. All right, now we've gone through the whole array once. And if we just glance at it, it's still not in order. So we have more work to do. So what we do is because our swap counter after this first pass is not at 0, we're going to start back at the beginning of the array and do it all again. And what's the first thing we do? We set the swap counter to 0 and select our first frame. 2 and 1, they're not in order. We're going to swap them and increment the swap counter. Boom. Slide our frame. 2 and 3, they're in order. We're just going to slide our frame without incrementing the swap counter. 3 and 5, they're in order. We're slide our frame without the swap counter. Now 5 and 4, we have to swap them, and we're going to increment the swap counter to 2. 5 and 6, they're in order. All right, so we finished the second pass. This time it only took 2 swaps. So what are we going to do? We're going to set it to 0, pick our first frame. 1 and 2 in order, no action needed. 2 and 3 in order, no action needed. 3 and 4, they're in order. And so is the rest of the thing. So we get to the end and our swap counter is 0. Well, that's great. That's our ending condition. And now the worst case scenario that we get here is that the array is in perfect reverse order, and we have to go through many, many times swapping every one. That takes a long time. That's the maximum. So our order, our big O for this, as we talked about in lecture, is n squared. And the best case scenario is that the array is already perfectly sorted, and we only have to go through once. And so our omega, our big omega for that is just the number of elements in the array, or the number of comparisons we make, which is n. The order of it is n, just a single n. So this is not the most efficient of our algorithms, but it is a classic. And we have to understand how it works and be able to implement it really without thinking about it. It's one of the very classic things. It works fine for small problems, but it doesn't scale well because of the big O of efficiency. And that's bubble sort, and that's all I have to say about that.